We're about to move to higher dimensional systems, and so to be prepared for that, I just want to provide a linear algebra review. So the first thing to review is how to multiply a matrix and a vector. So we have a matrix A, B, C, D, and a vector X, Y, and when we multiply them, we're going to get a vector, and we do a row of the first thing times a column of the second thing. So we'll have A times X plus B times Y as our first entry, so it's going in the first row and the first column, but there's only one column, so it will go in the first row and the only column. And then the second row times the first column gives us C times X plus D times Y. That goes right here, so that's how we multiply a matrix and a vector. You might recall that there are things called eigenvalues and eigenvectors, so now we're multiplying a, b, c, d times some particular vector uv, and for some special set of vectors of this system, this product will actually just be equal to a constant times uv, and so that's saying that whatever this matrix does to uv, it simply stretches it and leaves it in the same direction that it was initially in. And this is for some complex number lambda. So in this case, we call uv an eigenvector, and we call lambda an eigenvalue of this matrix. How do we find eigenvalues? Well, we've just given this definition for what they are, and now I'm going to bring the lambda v to the other side of the equation, so the matrix times v minus lambda times v is equal to the 0 vector. That would be 0, 0. And actually, a constant times v is the same as this matrix times v. If we were to multiply this matrix out times v, we'd see that these two things yield the exact same vector. And so I'm able to write this as matrix times v minus matrix times v, which means we're going to be able to take the difference of these two matrices. So when we take the difference of these two matrices, we have a minus lambda b c d minus lambda times v is equal to 0, where lambda is an eigenvalue and v is an eigenvector. So v is mapped to 0 by the linear transformation represented by this matrix. And if the transformation is a one-to-one transformation, then only the 0 vector would map to 0. But v is some non-zero vector, so that's telling us that this transformation is actually not one-to-one. Instead of being one-to-one, it must be a singular matrix. It must map multiple things to 0. And one property of a singular matrix happens to be that the determinant of that matrix is equal to 0. So we know from the fact that it maps a non-zero vector to 0 that the determinant of this matrix must be 0. And that's going to allow us to figure out values for lambda that do actually make this matrix singular. So the determinant of a minus lambda b c d minus lambda is this expression, a minus lambda times d minus lambda minus b times c, and that simplifies to lambda squared minus a plus d lambda plus ad minus bc. So this thing needs to be equal to 0 for lambda to be an eigenvalue, and thus for this matrix to be singular. And I just want to note in this equation that a plus d is the trace of the matrix A, B, C, D, and AD minus BC is the determinant of the matrix AD minus BC. So we can rewrite this quadratic for lambda in terms of the trace and the determinant of the original matrix. If we rewrote it that way and solved for lambda, we would find that there's two possible values for lambda, since we're in 2D and we're solving a quadratic, and they're related to the trace and the determinant. So we have the trace over 2 plus or minus the trace squared minus 4 times the determinant, the square root of that, all over 2. These are the two eigenvalues. So given the trace of a matrix and the determinant of a matrix, if we knew this expression, we could find the eigenvalues. Here's an example. We have the matrix 1, 2, 2, 6. The trace is 1 plus 6, which is 7. The determinant is 1 times 6 minus 2 times 2, which is 6 minus 4, which is 2. And so lambda is the trace over 2, plus or minus the square root of the trace squared, minus 4 times the determinant all over 2. That gives us 7 halves, plus or minus the square root of 41 all over 2. I should have vetted this matrix for nice numbers before I did this, but that's okay. We'll live with these kind of ugly numbers. Now we're going to check that if we plug in those eigenvalues, we do actually get the singular matrix that we expected. That will confirm that all of our math was correct. So I plug in the eigenvalues, and now I'm going to start a row reduction process. So I'm going to multiply this upper row by 2 and this lower row by 5/2 plus or minus root 41 over 2. And I'm going to do that to try to match this first term in the two rows. So there was a 2 here, so I'm multiplying this thing by 2, and there's this negative 5/2 minus plus root 41 over 2, and so I'm multiplying this thing by the negative of that, times 5/2 plus minus root 41 over 2. And when I do that multiplication, this negative 5/2 became a negative 5, this root 41 over 2 became a root 41, this 2 became a 4. And then this 2 times that kind of ugly expression gave us a 5 plus or minus root 41. That's good. These initial two terms match, which is by construction. And then we get this 5/2 times the 5/2 gives us a 25/4. The cross terms cancel because the signs are minus, plus, plus, minus. And then this outer term gives us a 41 over 4. And so we just need to simplify this, and we're hoping that we'll get I guess we're hoping for a negative 4. Indeed, when we simplify this, we do get negative 4. And so these two rows are now very visibly a linear multiple of each other. This row times negative 1 gives us this row. So this row reduces to just the upper row and a pair of zeros, meaning this is very visibly a singular matrix. And so that has confirmed that these were the right eigenvalues for this matrix.